Let us continue our discussion on lecture 3. In the first part, we discussed fixed bias circuit. We saw how operating point is fixed using a fixed bias circuit, and we also discussed the disadvantages, its dependence on temperature and dependence on the parameter beta. Now, a small modification is made for the fixed bias circuit, and we are going to connect the collector to base bias circuit here. So what is a modification done on fixed bias circuit? Initially, this connection from RB was to the voltage source VCC in fixed bias circuit. If you change that connection to collector circuit, that is, you are connecting it after RC to this point. From the VCC, we have changed the connection of RB to the collector side. So the base resistor is connected to the collector instead of connecting to the battery VCC. This circuit is known as collector to base bias circuit. So let us form the equations for collector to base bias circuit. VCC equal to RC into IB plus IC, that is a drop across RC, plus IBRB. Along this, IB is flowing in this direction. So the input side, if you form the Kirchhoff's voltage law equation, you get IBRB term here and plus VBE. Alright. So this equation, when you modify, you get an expression for IB as VCC minus ICRC minus VBE, the whole divided by RB plus RC. Okay, this is the expression for IB. Now, you can see VCE equal to VCC minus IC plus IB into RC, or VC is approximately equal to VCC minus IC RC. Since IB is very much less than IC, we can make this approximation. Now, substituting this expression, that is for VCC minus IC RC, if you substitute VCE, this expression, you get IB in terms of VCE and VBE. That is IB equal to VCE minus VBE by RB plus RC. Okay. So with this expression, let us see what is happening to the temperature dependence of this biasing. So what happens when temperature rises? So as temperature rises, you can see the reverse saturation current is increasing, which is causing an increase in ICEO, and as ICEO increases, you can say that IC will increase. Why? Because IC equal to beta IB plus ICEO. So as ICEO increases, again IC will increase. After that, what happens? When IC increases, we have this expression VCE equal to VCC minus ICRC, which means as IC, this term increases, VCE will decrease. That is shown here. From here, it moves to this point where VCE is seen to be decreased. As VCE decreases, IB will decrease. Why? We have this expression for IB. IB equal to VCE minus VBE by RC plus RB. Or as VCE decreases, this term decreases, which means IB will also decrease. If IB decreases, what happens? This base current is lowered, which will reduce the increase in collector current, or our collector current comes back to this region. That is, it is not that much increased, or the increase is not appreciable when compared with the fixed bias circuit. So this mechanism, there is a mechanism in this circuit because of which the collector current is not allowed to increase rapidly, or there is a tendency in the circuit to stabilize the operating point at the same VCE and IC even if temperature changes. Once you have fixed this operating point, as temperature changes, it is still stabilized at that operating point. IC is not varying much even when temperature changes. Now, collector to base bias circuit. What are the features? you can see that there is a feedback which is existing in the circuit. From the collector, you are actually taking a feedback to the base through RB, isn't it? The base current is dependent on collector voltage. This dependence nullifies the changes in base current. Since it is like a feedback taken from the collector circuit to the base, it is known as voltage feedback bias circuit. This collector to base bias circuit is also known as voltage to voltage feedback bias circuit. Now, when a transistor with new beta replaces the existing transistor, what happens? We saw temperature dependence. It is appreciably improved compared to fixed bias circuit. What about beta? So if let us determine the operating point, okay, we'll write in terms of beta, the base current in terms of beta. So VCC equal to RC into IB plus IC plus IB RB plus VBE. This is the equation of the input side when it is connected in collector to base biasing mode. Okay, so VCC equal to, you are replacing IC with beta IB, then you get an expression like this, RC into beta IB plus RC plus RB into IB plus VBE. So VCC equal to VBE plus, what are the terms, what are the factors of IB? RB plus beta plus 1 RC, or IB equal to VCC minus VBE by RB plus beta plus 1 into RC. This beta plus 1 is approximately equal to beta, or you get VCC, and you can neglect VBE also. So you get an expression for IB as VCC divided by RB plus beta RC. Okay, so this is the expression with beta term here. We are going to see what happens. So since IC equal to beta IB, we can determine the collector current using this expression. That is IC equal to beta IB will give you the value of IC. This IB you can get from VCC by RB plus beta RC. Now to determine the collector voltage, again we have the same equation, VCE equal to VCC minus IB plus IC into RC, which is approximately equal to VCC minus ICRC, since IC is very much greater than IB. Okay. Now compared to fixed bias, variation in IC with beta is also lesser. We saw there is a 150%, there is a 50% increase in IC when beta is changed in the previous problem which we discussed, isn't it? So there is no much appreciable change in IC compared to fixed bias circuit when beta is changed. Let us see this and understand this through a problem. So in this problem, you are asked to calculate the minimum and maximum collector current in this figure if the beta of the transistor varies within the limits indicated. Okay, so let us do this. So what is the expression for IB? We just saw now IB equal to VCC by RB plus beta times RC. Okay. So first we'll take the value of beta equal to 50. When beta equal to 50, what is this IB? You will get it as, this VCC is given as 20 volt, RB is given as 200 kilo ohm, 10 raised to 3, plus what is beta? 50 into RC is given as 2 kilo ohm, 2 into 10 raised to 3. If you simplify this expression, you will get it as 66.5 into 10 raised to minus 6 ampere, or 66.5 microampere. Okay, now what is the collector current? Collector current in this case is IC equal to beta times IB, which is equal to 50 here, isn't it? 50 into 66.5 into 10 raised to minus 6, and you get it as 3.33 milliampere. Okay, now we have to find out the second case. So beta equal to 200. So you are asked to find the minimum and maximum collector current. You found out the minimum collector current when beta equal to 50. What about when beta equal to 200? When beta equal to 200, using the same expression, if you calculate IB replacing beta, you get its value as 33.33 into 10 raised to minus 6 ampere. Okay, and with the same expression IC equal to beta IB, substituting this IB and new beta value, beta is 200 and IB is this value, you get it as IC equal to 6.66 milliampere. So what can you observe from this problem? So this is the minimum value of IC, this is the maximum value of IC. What can you conclude from here? See, the beta has increased 4 times. Beta was 50 and now beta is 200. So beta has increased 4 times. The base current is halved, isn't it? The base current was 66.5 microampere here, but when beta is 200, the base current is halved. And the collector current is becoming double. Collector current was 3.33 milliampere. Now it is doubled. Okay, whereas in fixed bias circuit, if beta had increased 4 times, the collector current also would have increased 4 times, which means with change in beta there is increase in collector current, but it is not as much as in fixed bias circuit. So you can take down this problem as homework. I couldn't place the figure here. I'll draw the figure here. So you have a 10 volt VCC, then an RC equal to 500 ohm and RB equal to 500 kilo ohm, and you are applying this to your base, and this is the feedback you are taking to base, and this is your collector, and this is the emitter, and emitter is connected to ground. Okay, so this is a transistor with beta equal to 100. Take down this question as a homework. You have to find the emitter current in the circuit. Also calculate VC. What is VC? The collector voltage. VC equal to VCE. Do this problem as homework. Now let us conclude our discussion. Though there is an improvement from fixed bias circuit, this collector to base bias is seldom used. That is because you are taking a feedback through RB. So if you apply AC signal, you know this transistor is used for amplifying AC signals. So if we provide an AC signal at its input, it is causing a feedback, AC feedback also. This RB connection from collector to the base is causing an AC feedback also. So ultimately this will reduce the voltage gain of the amplifier, and therefore proper signal amplification is thus affected if you use a collector to base bias. Okay, operating point fixing, then dependence on temperature and the beta variation. These are the 3 points we have to discuss when we consider any biasing circuit. But in this case, since there is a feedback, we have these disadvantages also. That is why this collector to base bias is also seldom used. So we need to go through further improved biasing circuits, which we will discuss in the next lecture. So for the time being, I am stopping here. Thank you.